Hi, I'm Tim Fox from Elephant Scale, and I'm going to talk today about Spark 2.x, the machine learning RDD API versus the new data frame API. And please go to this URL that you see on the upper right-hand part of the video, the bit.ly URL, and that will redirect you to the blog post and the solution and lab files that you can have with this particular exercise. Okay. Machine learning in Spark. So the Spark ML library provides lots of algorithms that we can use for performing machine learning at scale on our big data. Has a language support with Java, Scala, Python, and R, and provides distributed execution on our machine learning problems. And it includes lots of common machine learning algorithms like classification and regression models, linear models, decision tree learning, collaborative filtering, K-means clustering, and many more. Now, Spark.MLLib is the original API that existed from Spark 1.x, and it's built on top of RDDs, resilient distributed datasets, which are the base data type of Spark. Now, Spark.ML namespace provides a newer, higher-level API that was built on top of the data frame API, which is for constructing machine learning pipelines. So MLLib is slowly migrating to this new API, Spark.MLLib going to Spark.ML. And the new feature that this provides is the new pipeline API, which is borrowed from Python's scikit-learn package. Now, the basic types of the Spark ML is vectors. So this is basically common to both Spark MLLib and Spark.ML. And they consist of a collection of double values. And these can be either dense or sparse. And that's up to us, depending on the nature of the data, whether we have dense data or sparse data. And we have a factory method called vectors that is going to allow us to create these vectors programmatically. We also have a label point that is able to provide a label associated with a vector, and we use this a lot for regression and classification training. And we also have a matrix, which is a 2D grid of double numbers, can be sparse or dense, and a distributed matrix as well. Now, if we want to create vectors, we can use either the vectors.dense or the vectors.sparse factory methods, which will then generate the vector type, which will be able to give us the vectors we need for performing the machine learning algorithms we want to perform. Now, the new API has a class called VectorAssembler, which uses the same types, dense vector and sparse vector, as the older MLLib API. But what this does is it transforms a source data frame to another data frame by either adding or appending to a features column. So, for example, if we have, say, two input columns from our source data frame, MPG and cylinders, and we want to transform that, we can set the output columns, that would be features, to contain a feature vector that would then contain those two items. We call this feature extraction. And the VectorAssembler class makes this much easier to do than in the regular MLLib API that we had back from 1.0. And what it does is it actually transforms our source data frame into a new data frame with the feature vector column added. Now, we're going to give an example here about running K-means clustering in the new Spark.ML namespace. So K-means is an algorithm which is the simplest algorithm actually for clustering our vectors into usable clusters. So what we do with this is we first convert our data into vectors, as we've talked about that before. Then we're going to perform a clustering run with a specified number of iterations, and then we'll evaluate the fit of the cluster. So is that a good run? If not, we're going to specify the number of clusters. The K in K-means means how many clusters we're expecting to see in our data. And often we don't necessarily know how many clusters we expect to see, so we would then specify a range of values of K that will try and evaluate our results. Once we feel like we have a good clustering run, we would then map each of our vector to its nearest cluster, and then we can group our original data by its corresponding cluster. And then any new data that we come in, we can then assign or predict those vectors to their nearest cluster. Now, as we said before, the first step in Spark ML is to turn the data into a vector. So we choose from either dense or sparse depending on our data. For example, if we have one hot encoding, we would probably use sparse. And we have to use numeric vectors. So if we have any kind of categorical or other kind of data that's not numeric, then somehow or other we have to convert that to doubles. And one way to do that is if it's a numeric value, you can use the .toDouble function. And once we have an array of doubles, we can pass it to vector dense or vector spark. Now, in the old API, we use the class KMeans, and that would generate a KMeansModel. We would call the train method on that, where we would pass in our RDD of vectors, pass in our number of clusters, and pass in our number of iterations. So since we have to specify the number of iterations, the question would be how many should we have? And it depends. If it's too low, we might get stuck on some kind of a local minima or maxima, getting bad results. Too many, and we end up wasting time. So we could try 10 to 20, for instance. Now, let me contrast this with the new API. So in this case, we also call the class KMeans, but from the ML namespace. And what this is going to do, again, it's going to transform our data frame with the features column. Remember, we got this from VectorAssembler. And then we're going to run KMeans on this resultant data frame. And so here you can see that we're specifying k equals 2, and then we're setting a seed. And then we're going to call the kmeans.fit on the old data frame. And then now the new cluster data frame will have a new column, which is by default called prediction, that will contain an integer just specifying what we are clustering that particular vector to. Now, once we have a clustering run, we should see how that performed. So we can calculate it using the WSSSE, which stands for within the set sum of squared errors. And so basically this is a cost function, which is the sum of all the squared distances of points to their cluster centers. So if we have our points all very tightly clustered around their cluster centers, then that's good. That means our WSSSE would be low. But if they tend to be scattered very far away, then that sum of square distances is going to be high. And that would indicate that it wasn't the best clustering run, and we might want to try a new value of k. So this WSSSE is going to increase necessarily with increasing values of k. But there's going to be a law of diminishing returns. So higher values of k are going to give just marginal gains. So we can iterate across k until we get good results. What we often do is called the elbow method, because obviously we can get very good low values of k of WSSSE if we have higher values of k. But what we want to do is we want to find the elbow on the curve. So where we've gotten most of the marginal gain or loss associated with WSSE, in this case, perhaps 6 or 8 would be good values of k, because beyond that, we're going to get little additional benefit. All right, so once we have our model trained, then what can we do with it? Well, in the old API, we used the predict function on the KMeansModel that returns an integer. Now, on the new API, we have a prediction column in the output data frame, and that's going to be the meaning of the result. So that, in other words, in this case, the cluster number. So 0, 1, 2, 3. So in other words, k minus 1. So if we ran k with value of 4, then we would expect to see cluster numbers from 0 to 3. So if we have new data that comes into our system, then in the new API, we can again call the .fit to that data frame that would create a resultant data frame with the prediction column. Now note that the new data won't affect the existing cluster locations. We're going to look at an example here in a Jupyter notebook in which we're going to be looking at the mtcars dataset. Now what this is going to be is basically some performance numbers on different models of cars. Now notice here we have some different models, everything from a Mazda RX-4 to a Cadillac Fleetwood. And so we're going to be looking at the MPG and cylinders for these cars. Only those two columns, just to make life simple. We're going to ignore everything else. And if you look at these, see if you can find any of your own natural patterns of the data. Perhaps, for example, we might be able to look at data in terms of maybe compact cars and full-size cars and mid-size cars, for instance. And there might be fits between the MPGs of those different car models and the number of cylinders that they have. Okay, so that's what we might do. Let's see what our KMeans run will do. I'm going to open up a Jupyter notebook that'll show us how to do this in Spark ML. So this is our Jupyter notebook here. And so what we're going to do is we're going to call this cell by cell. And we're going to see what kind of results we get. And this is going to be using the newer Spark ML data frame API, not the older RDD API. So again, you can go to the URL on the upper right part of the screen that will give us a blog post that will give us a link to this Jupyter notebook that you can run yourself. Okay. So let's try running this cell by cell. So we're going to be loading our VectorAssembler and our KMeans class from our PySpark. And I'm going to be loading my data set here, which is our mtcars data. It's just going to be a CSV file that I'm going to be loading. And I just loaded that into a Spark data frame, and now I'm going to show us what we have for our data. And remember, it looks very similar to what we had in the slides. We have different models of cars, and notice that we have different numbers there. Again, we are going to look primarily at the MPG and cylinders for that. So let's actually go down, and what we're going to do is we're going to get a smaller data set here, and we're going to do that. Okay, so we got a smaller data set here. All right, so let's actually get we'll get this on our smaller data set. So we'll call this, actually I'm gonna put this here on a small data set. And now I'm going to be generating using the vector assembler on that to get a feature vector here. Now the feature vector, we're going to look at this, and I'm going to show this, is going to show us the model name and of course our two columns that we're looking at. And now notice I have a vector class that's showing up here as an array, which contains the features, which in this case is just the MPG and the cylinder, but now put in our vectors format that we need to do for machine learning. Okay, very good. Now let's run KMeans. So I'm going to start with k equals 2. And so now I'm going to call the KMeans function here within Spark ML. I'm going to set my value of k to, remember, k is the number of clusters we hope to see in the data, and I'm going to call the .fit method on this KMeans to our feature vector. Remember, that's what I just generated right here, and it's going to have, importantly, our features, which is going to have our feature vector associated with that. Okay, so let's give that a try. So we're going to just run this, and then we're going to compute the cost, which is the WSSSE, the within set sum of squared errors. All right. So I'm running this, I'm fitting my model, take a minute here. All right, so I just got my WSSC, which is around 525. Now, as I stated here, this is not particularly good. We probably need to change K. So let's look at the, first of all, let's look at the transform data set. So what we're going to do here is this is going to be the data set that we now have run. And notice here we have a new column here called prediction. And in this case, the prediction column here was 0 or 1. And remember, we set k equal to 2. So let's see what we have here. So notice we have kind of a cluster here with we have kind of fuel efficient small cars like the Fiat, the Civic, and the Corolla. And they're in cluster 1. And we have big kind of gas guzzler 8-cylinder cars, Cadillac, Lincoln, and Chrysler here in 0. And then a lot of these Mercedes and other kinds of mid-sized cars, these seem to be just kind of split between 0 and 1. And we're not really, again, it doesn't seem like there's necessarily a clean division there. So this kind of also indicates that our value of k may have not been ideal. So let's go ahead and now run with a different value of k equals 3, and see what that gives us in terms of WSSSEs. So remember, k equals 3, we're doing the same thing here, and we're going to compute cost at WSSC. Okay, so now we have the transformed WSSSE, which now is 1.69, much better, about a third of the WSSE. So this is clearly a better choice. Now, what we could do is we could try running a whole range of values of k and plotting them like I showed you in the notes there, where we would plot those and then select using the elbow method an ideal model of k. And in this case, probably k equals 3 or 4 is probably going to be around where we're looking at. let's look at our transformed data frame here, and for k equals 3, and see what that gives us. All right, so let's scroll down here. What we have is we have a new transformed data frame. And notice now our prediction column is a total of 0, 1, and 2. Because remember, we ran with k equals 3, so that means we have 3 different clusters. So here we have the Civic and the Fiat and the Corolla, which is going to be our kind of economy model of cluster that we had before. And we also have our kind of bigger 8-cylinder cars here, which is, remember, the Cadillac and Lincoln, the Chrysler kind of fit in that category there. Now we also have kind of another cluster where we have mostly 4 to 6 cylinder cars with kind of middling MPGs. So that kind of corresponds more with our intuitive sense of that, where we're kind of talking about sort of a small economy cars, big gas guzzlers, and then kind of a middle cluster. And we could try running with maybe k equals 4 to see if perhaps, we get some better results. Maybe that middle cluster should actually be 2 clusters. Hard to say. So anyway, that's what we have. And we can try running this to our heart's content and run the elbow method. But I hope we've gotten a bit of an idea of what the Spark ML 2.0 data frame API is going to give us. It is much easier than the RDD API and gives us this kind of nice pandas-style data frame-oriented approach, very reminiscent of Python scikit-learn library, which will make using the new data frame API in Spark 2.x much easier and much more enjoyable for our machine learning problems. Well, I hope you enjoyed doing this exercise as much as I did. Remember, please go to the link here in the upper right-hand corner and try out this Jupyter Notebook for yourself. I hope you have a great time doing lots of machine learning with Spark 2.0. Thank you very much.